Industrial Revolution 4.0. Innovations in artificial intelligence, cognitive neuromorphic, machine vision, robotics, deep learning, and data analytics are enhancing and improving our quality of life. As intelligent machines learn from their environment and execute self-error correction in order to successfully complete a task and ultimately to optimize productivity.
The framework of this project is to illustrate and to present the control and driving mechanisms of robotic arms. And the main theme is to grab different size objects which has applications within the industry and other different working environments. The robotic arm is functional, is light in weight, and it provides different attachments and controls in several interdisciplinary that characterizes mechatronics between the notions of mechanical engineering and also artificial intelligence and cognitive computing systems. The artificial intelligence robotic arm and the infrared sensor system. The arm is a modular arm consisting of five to six rotary joints. In addition, the end effector, which acts as a grip. The rotating joints consist of joint for base rotation, for shoulder rotation, for elbow rotation, for wrist rotation, and also for grip rotation. The 6 servo motors are chosen based on torque for proper operation. The infrared sensor is a sharp and is a distance sensory device composed of an integrated combination of position sensitive detection and infrared emitting diode, and also the signal processing artificial intelligence circuitry system. The device outputs the voltage corresponding to the detection distance, and every rotational joint of the arm is controlled by several servo motors. These motors are connected to the microcontroller, which is essentially a neuromorphic CPU system, which is controlled by the methodology and the system software based on Python and C++. The sensor is placed in front of the arm above the gripper, so it can read the distance between the gripper and reflected surfaces. Methodology for controlling the artificial intelligence robotic arm. The control arm can be evaluated in many levels of logical abstraction. In the framework, in the context of this environment, we are mainly interested in high-level tasks of desired trajectory defined in 3D, three-dimensional task space. There are 3 phases. Phase 1 is the trajectory planning. Phase 2 is the inverse kinematics, and Phase 3 is the motor control, which I am illustrating in this video presentation. The trajectory planning enables the robot, in this case, in this specific application of the robotic industrial arm. So it enables the robotic end effector to move from an initial position to another position. This transition forms the basis for many high-level tasks like reaching objects or avoiding obstacles. I have implemented the correct trajectory and also defined the inverse kinematics for the system infrastructure. The remaining task is to issue the correct motor commands to the joints of the industrial artificial intelligence robotic arm. These motor commands produce torques that lead to desired accelerations and therefore to the planned movement of the industrial robotic artificial intelligence arm. So depending on the actual robot, many different actuators can be used to produce joint torques. The complex Python mathematical algorithms must be able to perform the projections, local regressions, and distance metric adaptations in an incremental fashion without storing the data. Therefore, the complex mathematical algorithm keeps a number of variables that hold sufficient statistics for the software algorithm to perform the required calculations incrementally. Kinematics studies the motion of bodies without consideration of the forces or moments that cause the motion. Robot kinematics refers the analytical study of the motion of a robot manipulator, formulating the suitable kinematics models for a robotic mechanism is very crucial for analyzing the behavior of robotic manipulators specific to artificial intelligence robotic systems. There are two different spaces used in kinematics modeling of manipulators. One is the Cartesian space and the other is Quaternion space, which is the transformation between two Cartesian coordinate systems that can be decomposed into a rotation and a translation. Two main solution techniques for the inverse kinematics challenges are analytical and numerical methodologies. In the first type, the analytical, the joint variables are solved analytically based on the given configuration data. There are two approaches in the analytical methodology, that is geometric and algebraic solutions. The geometric approach is applied to the simple robot structures such as 2, 3, 4 DOF planar manipulators. For the manipulators with more links and whose arms extend into 3 dimensions or more, the geometry gets much more difficult. In this case, algebraic approach is more beneficial for the inverse kinematic solution. Quaternion filtering and modeling systems. The Quaternion vector pairs are used as an alternative methodology for driving the robotic kinematics of serial manipulators. The successive displacements in the methodology provides a very compact formulation for the kinematics equations, and also to reduce the number of equations obtained in each goal position according to the matrix counterparts. The Quaternion mathematical equation Q is the sum of a scalar S and three-dimensional vectors V. It is a quadrinomial expression with real angle theta and an axis of rotation n equals Ix plus Jy plus Kz, where I, J, and K are imaginary numbers. It may be expressed as a quadruple. Q equals open parenthesis theta, comma x, comma y, comma z, close parenthesis, or as a scalar, and a vector Q equals to open parenthesis theta u close parenthesis, where u is equal to x, comma y, comma z. The kinematic robotic is characterized by the use of algorithms of reading points of 3D space, floating interpolation by a polynomial of the fifth order, iterative process of solving inverse kinematics tasks, dynamic feed-forward torque of each motor, and calculation of position control algorithm with a control loop. The sensor is able to produce three components of the required linear velocity of the TCP in three orthogonal axes, and three components of the required rotational rates, such as angular velocity about this axis. These technologies are used by industrial robotics for equilibrium, balancing, as well as orientation purposes. This video deals with kinematical features of intelligent robots, having a sensor located at the arm. A typical sensor might be a force-torque transducer or a camera located at the wrist section of the robotic system. With such robot, the motion commands are generated by the sensor, and the robot must execute them in real time. This requires that the robot algorithms include control in sensor-oriented coordinates rather than in world coordinates as in conventional robots. Oriented coordinates may be comparable in complexity to that required in conventional robots. With a vision sensor attached to the arm, the actual position and orientation of the target are detected. The required force is constant during this assembly operation. the sensor measures the actual force between the robot and the body and compares it to the required one. The error is translated into velocity command, which causes a motion that eliminates or reduces this error. The Jacobian in the sensor coordinate system. The resolved motion rate control can be used for a sensor coordinate system. In the case of a sensor attached to the arm robotic system, the required velocity of the tool is provided by the sensor. The relationship between the tool velocity given in the sensor coordinate system and the joint speeds, the reference velocity of the tool is obtained by detecting the deviation between the target and the actual positions of the arm with the edge sensor. Angles of the robot by having the position and orientation of the end effector. The inverse kinematics of a serial manipulator is more important than the forward kinematics, as it is essential to move the gripper of the robot to a required position with a defined orientation to grab an object in the position and orientation. There are two approaches to solve the inverse kinematics issue of a robot manipulator. That is mathematical and geometrical. The higher degrees of freedom requires the more complicated algebraic solution. So this segment is devoted to presenting the geometrical solution for the inverse kinematic solutions. The design methodology for the forward and inverse kinematic robotic system. First, moving the end effector to the robot to a specific location and orientation. Next, calculating the joint angles by the inverse kinematic solution, followed by changing the joint angles to the calculated values. Afterwards, getting the gripper position and orientation by using the forward kinematics solutions. And finally, computing the Euclidean distance between the initial position orientation and the final position orientation to get the error of the two solutions.